It's 1:35, so we'll get started. Any questions out there? Any discussion points that people want to bring up before we dive into today's lecture? Anything out there? Any issues? So I do owe you a homework. I will post that tonight. And if you're following along in the syllabus, you know that there's an end of semester project. Brianna reminded me about homework on Tuesday, and sorry, I'm just a little bit behind getting a couple of things out the door, but I will post that homework tonight. It'll be the usual. You'll have 2 weekends to work on it, so it shouldn't be much different than what you've experienced before, but you should start thinking about your final project. And the final project is a paper and a presentation that's outlined in the syllabus. And so you should start to think about what are your resources, what are you interested in, what do you want to learn more about. And so for those of you doing 3D printing for your thesis, this might be an opportunity to expand your lit review or write a small section on things that you want to talk about. If you're working on 3D printing in industry, you're welcome to dive into some topic that would be useful to you. But again, the papers in the project are really what you make of them. Find something interesting and learn about it, and then tell other folks about it. And so I'll start to help you get organized on those things, and that will be coming tonight as soon as I just get a couple last things written and uploaded here. So sorry for the delay. But that won't set you back in terms of due dates. And we have plenty of time. Okay, any other questions or discussion points that people want to bring up? So we started VAT photopolymerization last time. And so remember where VAT photopolymerization lies on the ASTM diagram. And of course, we're going to call this SLA once in a while, or you'll hear DLP, or you'll hear CLIP or HARP if you look up Azul. There's lots of interesting ways that people are approaching this, but we're using liquids and we're using light reactive photopolymer curing. That's the thing that ties this whole section together. So we watched a couple of videos last time. We'll watch a couple more videos this time, getting oriented to what this topic is. But this is now the type of chemistry that you should at least be conversant in order to understand what we're doing here. And this is the same or similar to polyjet. We talked about polyjet printing or material jetting in terms of the Stratasys or object technology for that. So this is very similar UV activated acrylate photopolymer curing. And so rather than discussing TG and TM and the thermal transitions of the polymers, what we're going to talk about is this idea that you can go from liquid polymers or liquid resins, you shine light on them, they undergo free radical polymerization, and you eventually end up with a solid, because in general for organic materials, unless they crystallize or unless you're talking about crystalline small molecule organics, liquids will be low molecular weight, and sometimes we also call them oligomers. And solids in general will be high molecular weight. And so this is interesting because if you think back to that TG plot way back at the start of the semester where the glass transition temperature was dependent on the molecular weight, basically what we're doing is we're transiting the molecular weight here, and we're not necessarily increasing or going through a TG in this type of polymerization. We're going through gelation, and we'll talk about a scientific definition of gelation. But it's kind of the same idea that the material, as it builds molecular weight, it gets harder and harder and harder because the molecules get longer and longer and longer. So we're crossing that point from liquid to solid in photopolymerization. And in order to do effective vat photopolymerization 3D printing with this chemistry, this has to happen quick. Usually 50 to 200 milliseconds. That's all the light is on for, and we'll see some, oh, hold on. Well, Zoom is having issues today too. Let me go back. All right, let me try this. Oh, let me share my screen first. Well, this might be an interesting talk without any slides. Let me see if I can get back to what's going on. Maybe it's a PowerPoint issue. Bear with me. Okay, one more time here. Always something new. All right, screen broadcast is going. There's the PowerPoint. Okay, well, just must be one of those things. But anyway, this process happens really quickly. And so initiation, where we shine light on this photo initiator, and we're just going to show benzoyl peroxide here, but I'll show you a bunch of different photo initiators in a little bit. When you shine a UV photon on benzoyl peroxide, it splits to form two radicals because this molecule is symmetric. So you actually get two of those things. That falls apart and forms this benzene or aryl type radical here and gives off a little bit of CO2. There isn't that much photoinitiator in these resins, and so the CO2 doesn't really come out as bubbles. It's just dissolved in the resin. And then after initiation, so these are the initiation steps right here, that happens very quickly on the order of microseconds. Then you have this step called propagation. And propagation is where you build molecular weight. Because what you're doing is this radical, so anything with a dot, for those of you that haven't studied organic chemistry, anything with a dot is a radical, and we just call it a free radical because it hasn't reacted with anything yet, will propagate or will react with this acrylate. And so I guess formally in the nomenclature of free radical polymerization, the first monomer reaction is still part of the initiation step. And then once you have a free radical or an active center on the first monomer after it reacts with the photoinitiator, then you have propagation. But the idea of propagation is you build molecular weight, and this free radical or this little dot, this active center right there, reacts with subsequent monomers or since this is an R group, R means it can be a lot of other things as well. Those can be oligomers too. And so SLA recipes tend to have both monomers and oligomers in SLA resins. If you've ever seen an SLA, let me make that an L. If you've ever seen or used an SLA resin, they're kind of viscous. They're not quite as viscous as honey, although some might be, but depending on the mixture of monomers and oligomers in that SLA resin, the viscosity can be adjusted, the mechanical properties can be adjusted. You'll see the material character in terms of hydrophilic, hydrophobic, flexible, silicone-like. That can all be adjusted depending on the character of the oligomers. And so this recipe, whatever you put as R right here, so, and this slide's getting crowded, I apologize for that, but let me just write down here, R is used to determine material properties. And so if you're a little lost on the organic chemistry, you can think about it, and we will revisit this over and over, because we're going to look at different monomers, different oligomers, what they do, what their function is, what's the difference between a flexible SLA resin and a stiff SLA resin. And so we'll build up this story slowly, but this is the sort of organic chemistry picture of how this works, and it's all UV activated acrylate chemistry. So in all of the resins that you can buy right now for vat photopolymerization, they all do this. They have some different photoinitiators, and they do have different R groups, of course, but this is the basic picture. Even though that's a little bit of a busy slide, it starts to get you familiar with the process and now the organic chemistry. Any questions on that? Okay, for some of you that have taken a lot of polymer chemistry classes, this is no big deal. But if you're a mechanical engineer, we'll try and make this as user-friendly as possible. So the way to think about what may work in SLA resins, especially when you're investigating conventional SLA resins, things that you can use in printers now, is you really want to look for groups that look like this. So this is an acrylate. And because there's one on each side of this thing, this is called a diacrylate. And so now this hydrophilic PEG, and this is polyethylene glycol, because this part is PEG right here. You notice that, let me erase a little bit of this circle right here. You'll notice that N is shown right here, marking the parentheses. So N will specify number of monomers, and that will specify the molecular weight. So you might be able to buy, or you can buy, PEG diacrylate 600, PEG diacrylate 900, PEG diacrylate 300. So when you look in the catalog of all the different PEG diacrylates, it's saying, okay, this is PEG, polyethylene glycol. It's a diacrylate, which means that you have an acrylate on both ends of the chain. And the 600, the 900, the 300, etc., are the grams per mole, which is related to the N. And so right away, you can see that you can now change the distance between reactive centers in this PEG diacrylate by changing the molecular weight, or by changing the oligomer weight. And so just by investigating the different chemicals that are available for construction of these SLA resins, you can start to get different properties. And we'll talk about why molecular weight matters in this sort of cross-linking type resin in a little bit. So here you have a triacrylate, and anything that has more than 2 functional groups on it is going to cause a lot of cross-linking. So you get cross-links with diacrylates too, because you grow polymer chains from both ends like this. But you're going to grow lots of polymer chains. They're going to come together and cross-link polymer chains together in the network. So we tend to call those cross-linkers. And you see the molecular weight in the center here is not very high. So this serves as a gelation center or as a cross-linking center for whatever chemistry we choose. Here's, well, acrylchloride is special because it's not, it doesn't look exactly like an acrylate, but that chlorine functions a lot like the oxygen. So that's a functional monomer. Butyl acrylate right here. It's the same thing. Epoxy diacrylate, this thing right here, comes from epoxide ring opening, so that starts to look like epoxy. You have silicones, so PDMS is silicone. And then you also have a lot of different methacrylates. And methacrylates have this methyl group right here. And we're not going to go deep into the polymer chemistry, but methacrylates react a little bit more slowly than acrylates do because that methyl, whoops, sorry, I forgot the L. That methyl group slows things down a little bit. And so really recipes are tuned depending on what chemistry people might want and whether you want acrylates that react quickly or perhaps some molecules you want to react a little bit more slowly. In your resin recipe, you might use methacrylates. And so it just depends on how the resin is formulated, how your printer is working, things like that. Any questions on this part? We'll come back and revisit specific examples and how these resins are made, but I just want to give you the broad overview before we go into a lot of details here. Any questions so far? Okay, we'll keep going. It looks like screen sharing is still working, so that's good. So in terms of the photoinitiator, the photoinitiators can be complicated, and usually they're denoted just with their acronyms, but you can look up the chemical structure of all these different photoinitiators. And what's interesting is that they all have different max absorbances where they absorb the most light. And you really want to try and get your irradiation focused on what the max absorbance is. So this BDMM, whatever that is, we can look up the chemical structure of that. We would really like to irradiate here or here. So you really want to activate or irradiate photoinitiator at strong absorbance peaks. And this is now what's going to increase your efficiency of photoinitiation. So absorbance spectra, so this is what the y-axis isn't labeled, but this is absorbance. And so higher numbers are more absorbance. And if you look back at this carbon paper right here, wherever that plot is, they talk about the photoinitiator absorption coefficient. And they're talking about the incident photon flux as well. And so the photon flux is how bright the light is. So how many photons are you sending in to the resin? And then the photoinitiator absorption coefficient is related to how many of those photons are going to be turned into free radicals. Because just because you shine light on something doesn't mean you get any free radicals. You have to absorb that photon, that photoinitiator needs to break apart, it needs to form a free radical. There's an efficiency that goes along with that. But you have your highest photoinitiation efficiency where the absorbance of the molecule is the highest. And so the other cool part about photoinitiators is you see that the max absorbances can move around. And you know that you can tune lasers or laser diode to match photoinitiator absorbance. So that's very interesting. So if you have an SLA printer, say with a purple-violet diode that illuminates at 405 nanometers, you just need to go and find a photoinitiator that absorbs at 405, or at least close to it. And so maybe 384 is close enough, although you'd have to check it out. Or if you have a printer that has a laser that illuminates at 325, you have a choice of a few different photoinitiators. And the photoinitiator you choose will depend on stability, cost, what has a high photoinitiation coefficient, things that are known in the literature. And you'll see people use similar photoinitiators in all the different experimental recipes, because those are the ones that tend to work. It's what industry has used for UV curable coatings for a long time. And so there are some proven out photoinitiators that we'll talk about. But as you start to think about how resins relate to whatever printer you're working with, you need to make sure that your printer illumination is working at the right wavelength for the photoinitiator that's in your resin. Any questions on that? Okay, so we will continue to build up the organic chemistry of that photopolymerization, but I don't want to give you 3 lectures on organic chemistry because that will make for some dry discussion for some of you. And so just like we did with thermal 3D printing, material extrusion, and SLS, we're going to go back and forth between materials and process a little bit to bring all of these ideas along together. So these are just some examples, so you can check out these. These examples are from my lab, where you can formulate flexible resins, you can formulate ceramic resins, you can do lots of different stuff. You can even add additives. If you want to check this out, this is a photochromic where you shine light on this, and I think Locke might have made this in my lab, but this is cool because you can do lots of different things with these resins. And so we're going to talk about these resins, and there's lots of good guides for how to do SLA printing and what's available from industry, because these resins in some cases are difficult to formulate. New resins are difficult to print on whatever SLA technology you have, but it turns out, just like we studied 10 or 15 different polymers in the thermal polymerization, in the thermal 3D printing part of the class, there's at least that many resins, if not dozens of resins that are available in the marketplace for SLA. So you can check out the online guides. And one cool thing about this is if you look up what's available for 3D systems SLA printers, they have a really nice section on all the different strengths, hardnesses, etc., heat deflection temperature, which of course is not quite the same thing as TG, but it starts to get, is related to TG for their stereolithography setup. And they sell these resins under designations like ABS Light. So there isn't a single molecule of ABS in any of these resins, but the properties of these resins that are made using photopolymerization, the hardness, the modulus, the flex, etc., is similar to ABS. And lots of people are familiar with the properties of polycarbonate or ABS or polyethylene, etc. We sort of have a sense, if you've worked with plastics, you have a sense for what the properties of those thermoplastics are like, because we use a lot of thermoplastics to design parts right now. But when you get into UV polymerized resins, it's difficult to say that this is an acrylate polymerized resin that has a mixture of a few of these different monomers and the properties are like this. You really want to compare it to things that people know about. This is silicone-like, or this is polyurethane-like, or ABS-like. And so what these 3D printing companies have done is they've really tried to build families of resins. And so you can see all the different types of resins here that have similar properties to ABS. And they've really tried to benchmark these to thermoplastics that folks are familiar with. But all of these are different liquid resins. They probably have 20 or 30 different components, and we'll talk about a lot of those different components other than just the oligomer mixture. And they have the validated properties here, so you can do your material selection. So this is polypropylene-like, polycarbonate-like, polyethylene-like. And so that's really interesting, is now they're selling these cross-linked photopolymer resins that are described to be like thermoplastics, because we don't really encounter a lot of these types of materials, acrylate polymerized cross-linked resins. And so it's hard to describe what their properties are other than maybe silicones, which are usually cross-linked, and epoxies, which are cross-linked. Other than that, we don't have a lot of experience with what the properties of these things could be like. So my message on slides like this is don't get confused. You know, we're not going to have oligomers of polycarbonate. We're not going to have oligomers of polypropylene. We're not going to have oligomers of polyethylene. And we're not using acrylate photopolymerization to polymerize polyethylene or polymerize polycarbonate. We're really using other chemicals as a stand-in to give us properties that are like things that we're familiar with. And the exceptions are PDMS, silicone. We have to use silicone, but we can make PDMS oligomers, and some types of epoxies and polyurethanes. And so as we investigate different types of SLA materials and we look into what the recipes are for a lot of these different compounds, you'll see things that start to look familiar. But we're not making polypropylene or we're not polymerizing polypropylene using photopolymerization. It's a stand-in. So I hope that was clear. Are there any questions on that? Okay, for those of you that are interested in the details of the materials, we'll get there, so hang on, but this is just setting us up here to understand the ecosystem of that photopolymerization. The other thing that we're going to talk about is we're going to talk about post-processing. And so what carbon always says is that you use light to get the shape, and you use post-processing to get the properties. And post-processing can be additional UV cure, thermal curing, washing, etc. combination of the above. And this is one really nice example right here from Carbon's website. So they're using what's called a cyanate ester. And so we'll talk in detail about this chemistry because this is known, but what happens is that they take this cyanate ester, and this is the green part. So this is after UV. So after UV, we have a green part, and it's called a green part because it's still green. It's not treated like green wood or something like that, or a green body of a ceramic. And then this is after thermal. And so the UV photopolymerization that we just talked about activates all the acrylates and allows us to shape a three-dimensional object using acrylate photopolymerization, just like any SLA process. When we thermally cure the process, we take that shaped part, put it in an oven, and the thermal cure activates the cyanate ester chemistry that's not UV active. So this is two chemistries one is UV. Let's make it explicit. The first chemistry is UV to shape. And the second is thermal for modulus. So that's a crowded slide, but we'll revisit this again and we'll talk about exactly what cyanate ester chemistry is. But cyanate ester chemistry is not accessible by photopolymerization. And so in the mix of oligomers that Carbon uses for this material, they have acrylated cyanate ester molecules. And so they use the acrylates to shape the part using conventional SLA. Then they take that shaped part, put it in an oven, and then they activate the cyanate ester. And there you're able to do different sorts of chemistries at different times using different stimuli, which is really cool. If the polymer chemists in the class think about orthogonal chemistry or think about sequential chemistry that you can turn on at different times, they're doing exactly the same thing with these cyanate esters. This is also done for polyurethanes. It's done for a few different sorts of materials, and so we'll revisit this as we talk about specifics of materials. Why people are interested in cyanate esters is that they have very similar stress strain curves to GFN, which is glass filled nylon. And so glass-filled nylon is a automotive material, and so they put the glass filler in to decrease the water absorption and increase the strength of the nylon, but it's an engineering material that people are interested in. And so here you see the strengths on the order of 100 megapascal strengths and reasonable strain to breaks, although relatively brittle because cross-linked materials are in general going to have low tensile strengths. Oh, any questions on this before we move on? Like I said, we'll come back to this and we'll talk about post-curing and dual cure materials, but I want to introduce the concepts to get people thinking about these things as we go forward. Any questions or discussion points? All right. And again, we've talked about this before. We talked about this example actually in the composite section, if you remember this. And so this is a composite resin. And what this uses is an SLA photopolymer acrylate binder plus ceramic particles. And Tethon 3D was one of the first people out with the SLA ceramic resin. But now if you look at Formlab's website, if you look at Envision Tech, if you look at 3D Systems, they all have ceramic resins out for different sorts of applications. And this thing can be fired in a kiln just like a regular ceramic. So that's all very interesting. So this is both a composite and an SLA material using the type of chemistry that we've talked about. So the binders in this case are acrylate photopolymers, and they serve the same purpose as any ceramic binder, holding those ceramic particles together, but they're photopolymerizable, and so they might fall under the characteristics of a photoceramic, but this photoceramic can be put into a SLA printer and get a shape like this. So that's pretty interesting. Any questions on this? Okay, let me see if I can save this into the folder because I don't know that it's saving in the right spot. Oh, let me open it again. Oh, maybe I'm not going to be able to save it as anything here. There we go. Just so you have my notes online, and if this doesn't work, I'll upload it after class, but let me see if I can get it in the right folder now while we're here. And as we're waiting for this, you can switch over to lecture slide 8.1. So let me open up 8.1. Hopefully Box and Zoom and all the rest will be working together here for the rest of class. Okay, so we're going to talk about some examples. We're going to talk a little bit about gelation and talk about more how these resins are working. And we're going to see a couple of videos that we missed last time, and one really cool video to convince you that SLA is not just doing some things on the desktop, that there's big SLA going on like we saw before. So what we're doing, since we're using cross-linking and not thermoplastics, so thermoplastics, of course, are entangled chains with TG, TM, etc., all the things that we know about. In acrylate photopolymerization, we're really talking about thermosets. And so these are cross-linked. Sometimes it's spelled with a hyphen, sometimes it's not. There's a lot of different ways to spell cross-link. But these fall under the category of thermosets. And even though they have a heat deflection temperature and modulus and all the other material properties that we're used to, we're not using their thermal properties in order to process them. We're using this cross-linking reaction that we've described before. And so these cross-linking reactions can be thermal or photo cross-linkable. Just depends on what chemistry you're using and how you're going to tune that reaction. And so we're going to talk about how that process occurs. So in general, thermoplastics are finished polymers. They're made at a chemical factory and they're processed into pellets. That's the standard for injection molding. It's the standard for blow molding. You know, we've talked a lot about thermoplastics and how they work. There's a lot of thermosets out there, especially like epoxy thermosets that you are probably familiar with. Lots of thermally cured silicones are thermosets as well, or RTV. So if you've ever used a RTV silicone or an RTV polyurethane, that stands for room temperature vulcanizate. That's a type of thermoset. As a matter of fact, rubber tires are thermosets as well because they're cross-linked. And so there's just a different type of how the chains are interconnected, and that can lead to different properties. And of course, the big issue with thermosets is that they're difficult to recycle. You can't remelt them. You can only grind them up and recycle them as a ground polymer powder. And that's actually one of the biggest disadvantages of rubber tires. As you know, it's really, really hard to recycle tires. We tend to grind them up and make athletic tracks out of them or playgrounds or something like that. But there's only so many athletic tracks that we can make, and there's just massive tire dumps. It's a big waste problem that hasn't been addressed. But anyway, these types of classes of polymers tend to have different properties unless you can start to adjust the oligomer chemistry that we talked about before. So in general, thermoplastics tend to have higher strain to break, and thermosets tend to be more brittle because of the cross-linking. So if you think about how these diagrams here might deform, if you have these thermoplastic chains, they can ultimately slide past one another, and these chains can deform because the chains are not connected to each other by covalent bonds. And so that leads to this longer strain to break or higher strain to break in thermoplastic materials. Whereas thermosetting materials, because of the cross-links or because of this network structure, those chains can't slide past one another. That's why they're called thermosets. That's why they can't be recycled. And they tend to be more brittle materials, and they tend to have lower strain to break. So of course you can adjust the oligomer recipe in order to get flexible thermosets, and we'll talk a lot about flexible materials. But if you compare apples to apples, similar chemistry between thermoplastics and thermosets, the thermosets tend to be more brittle. But you can't shape thermoplastics in general at room temperature and get things that you might like to use in engineering applications. And so you can do room temperature processing of thermosets and get engineering parts. And so it's a trade-off, just like any sort of engineering design or material selection problem. You need to know the different aspects of the different materials and then make your selection that fits the requirements. And so if you're not, if you haven't studied a lot of mechanics of materials, or you haven't studied your mechanical properties recently, this just defines strengths, elongation to break, yield, etc. So these are just some vocab words that you might be interested in having in your nomenclature, so you know what all these properties are on the stress strain curve. So that's just an aside. I'll pause here. Are there any questions? Okay, we're going to watch a couple videos because there's a couple things that we missed in terms of describing the different process. And one of them is this video. And we're going to see exactly how this printer is operating in terms of the raster scanning to write in the different structures. And we'll compare that to a DLP carbon type printer where you see the whole layer being illuminated at once. So let me see if Zoom will cooperate here and allow me to show this video. And so first we'll talk about the Formlabs printer. And there's a couple key features of this. If you've never seen a Formlabs printer working before, this will give you an idea of what's going on. So let me start this video here.
From CNET, this is a first look at the Formlabs Form 2 3D printer. This is the second version of a printer that was initially conceived and funded from a Kickstarter campaign.
Okay, so the first thing that you see is that you see the light moving around on the print bed, and that's the raster scanning. So even though there's some reflection and some smearing of the light, this is a point source laser that's about 300 microns big in X and Y, and that's moving around, drawing in the different components of this part. So that's one thing to pay attention to.
Back in 2012. The company was founded by a couple engineers and designers from MIT who raised $2.8 million to build the first.
So the second part is you just saw the printer lift up the part from the window because this is bottom illuminated. It's going to wipe the window. It has a wiper to make sure it's nice and clean and there's nothing sticking there. And then it's going to put the part down exactly 100 microns away from the window to allow resin to be now between the window and the part to illuminate the next layer.
But today, thanks in large part to the feedback from the Kickstarter community and of course years of research and development, Formlabs is back with the Form 2. Now this one is very different from most of the 3D printers you see on the market.
Okay, and now you just saw the tray slide. The tray slides first before the part is lifted off to break the suction at the interface, and then it'll be wiped, and then it'll start again. So let me just back up a second here. You'll be able to see all the different stages of this wiping, writing, and sliding of the tray to break the suction.
In the Kickstarter community, and of course years of research and development, Formlabs is back with the Form 2. Now this one is very different from most of the 3D printers you see on the market today. Now those models operate kind of like 2D printers, but instead excrete molten hot thermoplastics from an actual print head. The Form 2, however, continues Formlabs' stereolithographic model. Stereolithography was actually the first 3D printing technique to be invented, and it uses a Blu-ray laser that actually traces part of the model image onto the surface of a bed of liquid resin. The orange cover blocks ultraviolet lights coming in that then hardens the sliver, and the process starts again as the completed object is slowly lifted out of the resin bath, layer by layer. As complicated as that sounds, I checked out an early look at the model at a briefing last month with the Formlabs team, and it's actually a very simple process for the consumer. You just unpack the printer, install the removable print tray, and insert one of the new resin cartridges directly into the machine like you would any ink cartridge on a 2D printer. The new model even adds a touchscreen display for managing print jobs and a Wi-Fi connection that'll automatically send progress updates to mobile devices in case you want to step away from the printer for a while or if you're planning to share it amongst several users. So why stereolithography? Well, one thing is that these printers can add a level of detail that standard fused filament printers can't, and that's whether you're printing something big or something super tiny like a ring. The ultra-high resolution also does a good job at hiding the individual layers of plastic from plain sight. You can barely even see the lattice pattern formed by the plastic layers, which really makes it seem like the objects were cut from one solid piece of plastic. You can buy the Form 2 right now for $3,500, which includes the 3D editing software, resin, and a finish kit for post-processing. You can read more details about the upgraded Form 2 in the full first take, but that's going to do it for me.
Okay. So we have that printer, and that's very interesting. And let's compare that just to the short video of the carbon printer to give us an idea, especially how the different printing routine works in terms of what the printer looks like as it's printing. So let's see how this goes. I think there's a little talking, and then they'll show some prints.
Hey Sean, you remember that video that made the rounds on the internet last year from TED about 3D printing?
The clip technology?
From the company Carbon, and it was a video of a piece being printed out of resin that basically looked like it was just coming out of the resin.
Like super speed.
Oh my God, and even though it was time-lapse, I think about 7x, it was much faster than any of the 3D printing technologies we'd seen before.
Yeah, it seemed like black magic.
Right, and well, we are here at Carbon where we're going to get a demo of their actual machine, the M1 printer.
Yes.
Super excited.
Me too.
Let's go check it out. Hey Kirk, it's great to meet you.
Nice to meet you.
We're very excited about this. So this is it. This is the M1.
Yes, our first product.
Wow, and it uses Carbon 3D's clip technology, which we saw videos of online. Yep. It's gone everywhere. Can you describe a little bit about what's going on, what the machine encompasses, and how it differentiates itself?
Okay, so what you can see in this is you can see the light is not flashing like it does in the Formlabs printer, or it's not raster scanning, so it's not moving around. This is a total 2D exposure. And even though this is sped up a little bit, this shows that there's no wiping step. You get relatively smooth pull of the part. And so this is cool because they're showing it in clear. And the image is changing in the projection here. That's, of course, how you change the part. But this is a lot different physics of the process compared to what we saw with the Formlabs printer.
From other printers that use resin?
Sure. So our technology, CLIP, for continuous liquid interface production, is a fundamental advance in 3D printing. And what it allows is for us to print very fast, without layers, in engineering materials. So all that together allows us to work with people who want to make real parts for production, as opposed to just for prototyping.
Right, which you can do also prototyping.
Correct.
So continuous printing, how does that happen? Because we've seen SLA printers where a laser goes by layer,
right.
And then there's a scrape process, and over time, over many hours, you get an object.
That's right. So SLA, as you know, has existed for 30 years, and it's a great technology for prototyping. Our founder looked at SLA and realized that there was a bug that could be a feature. He realized that you can get rid of layers if you control not only light, but oxygen and light. And up to this point, the SLA industry has thought about oxygen as the enemy. But if you make oxygen your friend, you can remove those layers and go really fast and use a much wider range of polymer chemistries to create these amazing parts.
Oxygen is something that inhibits the curing of
That's
resin.
exactly right. So a light turns your liquid into a solid. Oxygen prevents that from happening. And if you use sophisticated software to modulate the effects of both together, to make them work together, you can make these amazing parts.
So what kind of light are you using?
We're using UV light, and we use the same UV light that's used in other SLA approaches. But again, it's the combination of light and oxygen that allows this magic to happen.
To do it continuously, are you drawing the outline of the print? Is it all going one time?
So underneath, down in the cabinet here, we have what's very similar to a very high-performance desktop projector. We're projecting an image. Imagine playing a movie. So we take your three-dimensional structure, and we take its cross-section and project its cross-section into the bottom of this liquid vat. Then again, controlling both the light and the oxygen, you can get rid of those layers and make awesome parts.
Right, it's like basically a DLP projector.
That's exactly right.
Because the software still does slicing of traditional
Correct.
models. So you think of like a cross-section, like
Correct.
you said.
Yes.
But instead of drawing the outline or
Right.
drawing the inlay, it's just projecting that all at once.
Correct. That's right.
Does that also then inform like the bed size?
That's right. So we are launching M1 to get CLIP out into the world because we've got engineers and designers and business people who want to use 3D printers to change the products they make and to change the businesses they run. Right? Imagine you want to get rid of your spare parts warehouse, all these plastic parts just hanging out waiting for someone to need a spare part for your 2006 Toyota Matrix, which is the car that I drive. Right. That's a bummer to have to hold all those spare parts in inventory waiting for Kirk to call when he needs a new door handle, which is a problem I had just this morning. So instead what you want to do is you want to have a production quality 3D printer that can make that part at an appropriate quality for me to use in my real life. So that's what this machine is about, and we're really excited to show it to you today.
Yeah, and I think the best way to illustrate it is to actually get the demo.
Let's
so
do
let's
it.
start this. And the resin I think you have going here is your prototyping resin.
That's
which is
right.
the fastest printing one.
So we have a wide range of resins, some of which are for final parts and some of which are for prototyping. Now, as you know, when people are making real things, they go from concept, an idea, to a final product. And along that process, there are many different resins you might want. You might want to prototype first, then understand the model and its geometry. Then you want to go to production in a high-quality engineering resin. So what's happening right now, this is the build platform, and it's descending into this liquid puddle of resin. The light, when we get down here into the bottom, will project into the bottom of this pool of resin. You can think about this as a small fishbowl. It's a container of liquid with a transparent bottom surface. We're going to project through that transparent bottom surface, and we're also going to, with our physics and chemistry model, control the oxygen and its interplay with light. So now you can see that the build platform has descended into the pool, and you can't see this, but underneath we have our optimized projection system with UV light projecting into the bottom, projecting the cross sections in as we build the object. So the object is being built right now. You just can't see it because it's underneath the surface of your pond of resin.
So Kirk, this is super exciting,
Yeah.
and this whole process with this model and this material is going to take about 15 minutes, you said. So
That's
I'd
right.
love to use that time to ask you more questions about the technology outside.
Great, let's do it.
Okay, so you can check out the rest of that video, but that gives you a lot of interesting information on what carbon is all about. Oh, I don't know what's going on here. What carbon is all about and how their technology compares to other SLA or photopolymerization type of technology. And the rapid printing has been figured out. What carbon is really good at now is the different materials. So because they're polymer chemists or because they have a polymer chemistry focus, they're good at using different oligomers, at formulating different materials and getting really desirable properties. And we'll talk about that as we go forward here as this PowerPoint slide comes up. Let me see if I can get this going. One sec, bear with me. Okay, this might just take a second, but we're still on lecture 8.1. We're going to talk about, I think, gelation are the next set of slides. But this idea of different oligomers, we're still using, no matter what oligomer mixture we're interested in or what final properties we're interested in, whether it's a flexible resin or a rigid resin or even a ceramic resin, we're still going to do photo cross-linkable polymers, and they need to undergo gelation as we transition from a liquid to a solid. So rather than TG, which is the glass transition temperature that we talked about before, gelation, or the gel point, is when a liquid changes from liquid to a solid. That's called gelation, and that's a phenomenon that's been defined by how many crosslinks are built into the material. And we're gonna cover that as soon as these slides come up here. Hold on. 1 second, let me try it again. If I can't get my PowerPoint going, I have one more video to show you, but let's talk about gelation first. All right, let's see if this works one final time. Well, it might be that PowerPoint or Box is taking a break here, but the basic phenomena is gelation. And so when you define a liquid, liquids have viscosities. And so as you go from a small molecule liquid to an oligomeric liquid, the viscosity increases. So as you increase the molecular weight of the molecules that are in the liquid, the viscosity goes up. When you hit the gel point, that is the liquid to solid transition, and then solids don't have viscosities anymore. The viscosity is infinite, but the modulus starts to increase. And so you'll see an interesting plot where you see the viscosity increase, and then you hit the gel point, and then you'll see the modulus increase. And we'll cover that next time because it doesn't look like this PowerPoint is going to come up. But I want to show this one video from EnvisionTech talking about applications and what you can do with SLA. And this is in one of the application notes. And we'll talk about different applications for 3D printing technology as we go a little bit further. But this was a nice complement to thinking about, okay, now that we have 3D printing, what can we do with it in large scale? So let's watch this video and we'll see if PowerPoint comes back to finish off the class. But this is really cool because this shows you what you can do now with a 3D printing factory and how it's transformed an industry. So let's check this out.
It's great to help people hear better. Sonova is the largest hearing healthcare provider in the world. From this facility, they serve Phonak and Unitron brand. There's over 500 employees. It's a lean manufacturing facility.
At Sonova, we envision a world where everyone has the ability to just live a normal life, even if they have a hearing impairment, because of the kind of products we supply. What we produce here just isn't a product, it isn't a widget, but it's an individual custom-made item that someone is going to wear on their body, and it's going to make a huge difference in their life. And this all ties into the technology that we use to produce that.
Together with EnvisionTech, we collaborated quite intensively to bring this cutting-edge DLP technology into the on-demand manufacturing, rapid prototyping process, and we've done that successfully.
This is truly cutting edge because we're producing all of our products by 3D printing.
We needed to ensure that when we went 100% digital manufacturing, that we had a process that was easy to use and operate and produce very consistent shells.
We have over 100 EnvisionTech printers across the globe. We produce over 1 million shells a year. Each shell is customized for each patient.
We've been using EnvisionTech machines, I believe, almost 15 years, and it's been a very, very successful experience for us.
We are able to build blue and red material colors in one printer, and it helps our process to flow much better.
We have completely transformed the way custom hearing aids are made today.
Our customers, the hearing healthcare professionals, are going to take a silicone impression of their customer's ear. That impression then is sent in to us with a set of order instructions for what kind of hearing aid they want. That impression is then scanned so we can capture that digital image. That digital image is then moved to a modeler. The modeler now is designing not only the shell or the part that's going to fit in the ear, but they're laying out all the components inside that hearing instrument. We pass that then into what we call our shell lab. That's where our EnvisionTech 3D printers are. A build is created. The digital printer simply forms that shell. When that's finished, we pull all the parts for that instrument, and in production, they take that custom-made 3D printed shell, they take the electronics, they mate those together and seal that. After that is completed, it passes through a couple of different QC steps, including a full electroacoustic testing. And once it passes all that, it's ready to ship out to our hearing healthcare professional customer, who then fits that on the actual user of the device.
I'm very proud that we were the first to believe in that technology because we believe that this will be the cutting edge, the greatest and the best and transformational way of making hearing aids.
The products we provide to people are really making a difference in their life every day. So getting a hearing aid is a big deal.
Today, EnvisionTech technology is the standard in our industry. So the patients feel better. They're getting smaller hearing aids that fit better, that are retained in the ear better, that last longer, that have cosmetic appearance that's acceptable to them. It's a great cause to help people improve their hearing. And that's what we do. We help people hear better and live the life without limitations.
Oh, hold on. All right, let me see if PowerPoint's back. Oh, it's not. One more try. All right, one more try on screen broadcast here. All right, we're looking for 8.1. So after these couple lectures, you should be starting to get familiar with SLA and starting to get familiar with the relationship between the types of printing routines that are used versus the types of materials that are possible. And then what we'll talk about is how to put those together, what properties are possible with this type of technology, and then ultimately how we might be able to apply this technology to different applications, whether it's medical or hearing aids, as we just saw. So 10 years ago, there were no 3D printing hearing aids, and now 95% of the hearing aids out there are 3D printed, or whether it's jewelry or food applications or other applications of SLA. And so it looks like we're not going to have any more PowerPoint slides. And so I will stop talking a couple minutes early today, and I promise I'll pay you back a couple minutes in future lectures. But you should start to be developing some knowledge now that we've discussed a few different 3D printing processes. What's appropriate when? How might you apply these different 3D printing processes? And how does it matter for polymers and composites and constructing components of interest for different industries out of polymers and composites? And we'll continue on this vein next week when PowerPoint and Box is fixed. So are there any questions before we end lecture here just a minute or two early? Any things people want to bring up? Okay, well, I will get your homework posted, and you can continue to ask questions online or shoot me any interesting points you want by email, and we'll pick this up then next week on Zoom. Thank you very much. Bye-bye.
Bye, thank you.
Thank you.